Hello, hello, hello. I'm going to discuss with you the solution of a simple high school problem. I'm going to divide that into two parts. The first part will be the way that any high school student should be able to solve it, and many first year college students would also solve it that way. A double plus, if you solve it the way that I will show you, it's trivial. The question then is, have you really learned some physics? And that's really my task. Because my task is to make you see through the equations. And that's why I'm going to add a second part in which I will address what for me are actually the most interesting parts of this problem. Okay. We have here a solid ball, a ball. I was thinking I had in the back of my mind a bowling ball, but that's irrelevant now. We release that ball with no spin, only with a velocity in this direction, v0 times 0, on this horizontal surface. The object has mass m, we know the mass. The friction coefficient between the ball and the surface is 0.02. Friction coefficient is dimensionless. I make v0, and when I start it, 9 meters per second, 9.0, which is actually very close to the speed that people release a bowling ball. I looked that up on the web. The radius of a bowling ball is about 12 centimeters, and we will all use for g this value. The ball starts sliding. And as long as it's sliding, there is a frictional force in this direction which will torque it up. Therefore it will start to spin clockwise. Goes faster and faster and faster. And then there comes a time that the object is what we call in pure roll. And that happens when the speed, the velocity of the center of the ball equals omega r. If you have forgotten about this, you have to do your homework on that. When that happens, in the early part, when there is still friction and the ball is sliding, heat is produced because of the friction. The moment that it goes into pure roll, and by the way, also of course, the object will decelerate. The speed of the center, which started with v0, will go down and down and down. That's obvious. And the angular frequency, omega, or if you want frequency in hertz, will go higher and higher and higher, because it's being torqued up. Now there comes a time that speed of the center equals omega r, that is pure roll situation. From that moment on, there will be no longer any friction. The speed of the ball, of the center, will continue forever and ever and ever. And omega, that it has reached at that point of pure roll, will continue forever and ever and ever. And no heat is produced anymore, no energy is lost anymore. Now of course in practice, there's always air drag and there are always some imperfections in the surface, so surely the ball will ultimately come to a halt. But theoretically we could imagine that there are no forces, no air drag, and since the frictional force goes to 0, the ball will continue to go with the same speed forever and ever and ever, whatever that means, and omega at that pure roll will never change anymore. And now the question that I have for you, what is the frequency at pure roll in hertz? What is the distance at the moment that the pure roll is reached? What is the distance that the ball has traveled? And then what is the frictional force past the point of pure roll? And I already gave that away. I already told you. That frictional force goes to zero. That may be the hardest part for you to digest. Really goes to zero. So if you're ready now, we will solve this in a straightforward way and you will deserve an A double plus. Whether you've learned much physics then is a separate point. But that comes in my second part. So the frictional force is the normal force upwards, which of course is mg. I haven't drawn the normal force in there because the figure becomes too complicated. So that is n times mg, because n is mg and mu is the friction coefficient. So with the numbers that we have, a, which is the acceleration, which is the force divided by the mass, is 1.96 meters per second square. The moment of inertia of a solid sphere, the uniform mass density, is 2/5 mr squared. Notice that relative to this point, there is now a torque. A torque is the cross product between this position vector r, green down, and this F friction in horizontal direction. Since the angle here is 90 degrees, the sine of the angle is 1, so the torque, the clockwise torque, has a magnitude F times R or R times F, whichever you prefer. So the torque is I alpha. If you have forgotten about that, you should do your homework on that again. And alpha is the derivative of the angular frequency, omega dot. The dot means the first derivative of omega. So I omega dot is then the torque, the magnitude of the torque, which is the frictional force times R. It follows immediately from this that omega dot is 5/2 times A over R. And the 5/2 of course comes in because of this I. So we can calculate now what omega dot is, because we know what A is and we know what R is, and we find 40.83. Omega starts at 0, and omega dot is a constant. And so omega will now linearly grow in time. Omega will be omega dot times time. And that will continue until we reach pure roll, at which moment v, the speed of the ball, equals omega r. Now the speed of the ball is of course v0 minus at. A is constant. And so this v must now be omega times r, and omega is omega dot times t. So this v is now omega dot rt. And so now I can calculate what this t is at the moment that v equals omega r. And I call that t PR. PR stands for pure roll. And it follows immediately from this, if you combine that with what I found earlier, that the time that the pure roll starts is at 2v0 divided by 7a, which is 1.312 seconds. So now we're almost done, because we can now calculate what omega at pure roll is. You can do it in two different ways. You can either take this number 1.312 and multiply that by this 40, that will give you 53.57 radians per second. Alternatively, you can use this result and this result, so you find then that omega at pure roll is 5V0 divided by 7R, and that will give you, of course, the same answer. So this is 53.6 radians per second. Divide that by 2 pi, not mu, by 2 pi, and you get the frequency, which is your first answer, about 8.53 Hertz. So we're done with this. Now comes the second question. What is the distance that it had traveled at the moment that it starts pure roll? So I call this dPr to make reference to the fact that it's the moment that it reaches pure roll. Well, that is the classic high school equation, of course. V0, that is the speed at time 0, which is my 9 meters per second, time t, when it reaches pure roll, minus 1 half a t squared. And this a is that a. And so, since you know t, since you know V0, since you know a, you find that it has moved 10.1 meters, and then it reaches pure roll. The last question is, what now is the frictional force just after it reaches pure roll? I already told you. You may want to think about that a little more. The frictional force goes to 0. Now, so the frictional force goes to 0. If you have these answers, if you did the problem, you scored 100%. Have you learned much physics? I don't think so. I want to ask a few more questions. And I will start with the following questions. Notice, and you should pay attention to that, which is quite remarkable, that A, the time that it reaches pure roll, independent of m. A is independent of the mass. Omega dot, independent of the mass. Omega PR, independent of the mass. VTR, this V times TR, also independent of the mass. The distance traveled when it reaches pure roll is also independent of m. So all these quantities, 1, 2, 3, 4, 5, 6, are all independent of m. Isn't that strange? Well, maybe it is. Remember, when you have a pendulum, that the period of a pendulum is also independent of the mass. That too is not so intuitive, but that's often the case when you deal with gravity, that m often cancels out. Watch my lecture in which I roll objects down an incline. I do it with spheres, I do it with cylinders, with hollow cylinders, with hollow spheres. In all these cases, if you compare 10 different types of spheres, then the time that it takes to roll down is independent of the mass of the sphere, independent of the radius of the sphere. Not so obvious, but it's true. And I do a demonstration, I demonstrate that. If you have a solid cylinder, independent of the mass, independent of the length of the cylinder, independent of the radius of the cylinder, the time that it takes to roll down that incline is independent of mass, radius and length. So maybe you're willing now to digest the idea that all these quantities are independent of m. The time that it takes for objects to roll down an incline does depend on the geometry, on the mass distribution, where the mass is. And that's expressed by I, which is the moment of inertia. We had the I there too, remember? The moment of inertia. And that moment of inertia here refracts itself in this 5/2, in this 2/7, and in this 5/7. Let's look at the time that pure roll has been achieved. Forget the 2/7 for now. Just take V0 divided by A, because it is proportional to V0 divided by A, and A is mu G. Is that obvious? Yeah, I think that's obvious. If you make mu 0, there's no way, of course, that it will ever start to spin. There's no torque anymore, because there's no frictional force. So it's completely reasonable when mu is 0 that the time to reach pure roll will never happen, infinitely long. How about G equals 0? So you did this experiment in an area where there is the gravitational acceleration is 0. Well, then there is no friction. And if there is no friction, obviously it can never be torqued up. So again, the time will be infinitely long. Now comes something puzzling. If V0 is 0, the time that it takes to reach pure roll is 0 seconds. How can that be? It never reaches pure roll. Well, keep in mind that our definition of pure roll was that V equals omega r. And V at all moments in time, if V0 is 0, then V at all moments in time is 0. And so omega at all moments in time is 0. So 0 is 0 times r. And so the math says, sure, if V0 is 0, then TPR is 0, but it has no physical meaning. It follows from the fact that this is the way we have defined pure roll. Now comes my last question, which is a little bit more tricky. It also states here that the larger V0, the longer will be the time for it to reach pure roll. So now I will stop this recording. I will replace the batteries in my simple camera, and then I will continue this. And that second part, which is going to be part of these solutions, I find that the most interesting of all. And that all evolves from the simple question, is it obvious that when V0 increases, that the time that it takes to reach pure roll also increases? So, give me a chance to make the change, and hang on. By all means, hang on. Alright, so let's continue now to try to see through the equations. Because for me that's the most interesting. And so the question now is it obvious that when V0 increases, that it takes longer for pure roll to occur? You may say, well, yeah, that's consistent with my intuition, and I would agree with you, it's also consistent with my intuition, but I want to be a little bit more precise than just my intuition. Omega dot and A are both independent of V0. So omega will grow linearly in time in the beginning because omega dot is constant. So this is linear dependence. V is also linearly dependent on time. Since A is a constant, V as a function of time will also be a straight line. I have chosen, purely for convenience, but it's really irrelevant, I've chosen r equals 1 because then when pure roll is achieved, omega equals, V equals omega r, then V equals omega. But be my guest and choose V equals 2 omega or 5 omega or half omega, that's okay. You can change r any way you want to. I just now assume r is 1. So I plot now V as a function of time, which is the red line, and omega as a function of time. Omega starts with 0. Omega dot is the derivative. That's this angle. And so it will linearly grow. V starts here at V0. It's a straight line. And this angle, which is the acceleration, is A. And when the two meet, because r equals 1 in my case, omega remains the same and V remains the same. So omega at pure roll condition continues the same as it was in time, and the speed of the center of the ball also remains constant. Now let's suppose we make V0 smaller. Keep an eye on where the time is that we reach pure roll. So I'm now going to make V0 smaller. There you go. This now is V0. Omega in time is not changing because all I did, I only changed V0. You see, they now meet earlier in time. So it's immediately obvious from this plot that if V0 goes down, that the time to reach pure roll will also go down. If you have a hang-up on the idea that I have chosen r equals 1, then be my guest and choose a larger value for r, or let's say a lower value for r. If r is lower than 1, omega dot is larger than what I have here, so the green line comes at a steeper angle. The lower r, the larger omega dot. And then, of course, you reach pure roll when V equals the same as your new omega. And because r is not 1, you don't get a situation like this. But make that drawing and you will see that you come to the same conclusion, that if you lower V0, the time that it takes to reach pure roll goes down. So now comes the second part, and that is the distance as a function of time. This is, nothing is linear here. It's linear in t and linear here in proportional to t squared. So I made an effort to show you not only how omega changes in time and how the speed changes in time, but also how the distance changes in time. So if you're ready for that, what you see here is very important. I distinguish here three different parts, so to speak. In the beginning, this will be the way that d changes in time. When t reaches the time of pure roll, then of course d, the t's are now t pure roll. So this is before it reaches pure roll. This is at the moment that it reaches pure roll. And when t is larger than t pure roll, d will only change linearly in time because there is no longer any acceleration. V remains constant. V at that moment is of course the speed at pure roll. And so it continues linearly. And I have shown that also in a plot. So you see that here. Keep in mind that V0 was 9 meters per second, and if you remember, A was 1.96 meters per second square. I plot this equation here with the black line. Utterly trivial high school plot. D is 0, T is 0, and D is also 0 when T is 2V0 over A. That's the parabola. This angle here is V0. This point here, sort of an axis of symmetry of the parabola, is at V0 over A. Well, V0 is 9 and A is about 2, so this is about 4.5 seconds. When the time is 2V0 over 7A, that's the 1.31 seconds, that's the time that pure roll is achieved. So that's here. So you can substitute now this time into that equation, and obviously you find you 10.1 meters because we did that before. So once d is this high, the speed now is v pure roll, and that speed will no longer change. And so from this moment on, d will grow linearly in time with this v times t. That's this green line. Not that it is very important, but V0 squared divided by 2a for this value of V0, that maximum value of the parabola is at 20.7, which happens to be roughly twice this one. That's not so important now. What you may want to do, that is a little bit tricky for me to draw, suppose you double V0. If you double V0, this point comes twice as far. So this line is now here. This point is now here. But this point, this line, which is now here, is 4 times higher than this one because of the V0 square. So I would like you to draw a new parabola with the axis of symmetry, if you call that, here, which is 4 times higher than this one, and then do the same thing that I did. Of course, t pure roll will now also be twice as large as this one. It will not be 1.3 seconds, but it will 2.62 seconds because V0 has doubled. So that's going to be somewhere here. So draw then the dotted line upstairs until you hit that new parabola, and then where they intersect this dotted line with the parabola, you draw again your new green line, which you will see that that speed will be larger than this one. I thought that all of this will give you some interesting insight in what's really happening. Just to get some answers, some simple answers about 8.5 Hertz, about 2.1 meters. It's not very satisfying. It becomes satisfying if you see it in context, what happens in time. So I'll go over the basic idea. In the beginning, as long as there is slip, as long as the disk is skidding, omega will increase and the speed will decrease. There comes a time that omega V equals omega R, the friction goes to zero, omega will no longer change, no energy will be lost anymore, and V will no longer change. That's very, very basic. And you see that also in a beautiful way in this equation. I'm fairly sure that most of you will have all the answers correct, because if you have this, yeah, then that's correct. You can't be more correct than that. I decided to go one step beyond that, and I hope you will appreciate it. Have a nice day. Take care. And sure, of course, I want to be friends, and I want you to be my friends.